So I guess I'm on deck for the introduction. Susie,
Can you hear me, Ralph?
I can hear you just fine. Yeah, let me provide to the audience an introduction to Suzanne Dodd. She's going to be speaking next. She's the JPL director for the Interplanetary Network Directorate, which runs the Deep Space Network out at JPL. Has over 30 years of experience in spacecraft operations. She's got degrees in engineering and applied science from Caltech, math and physics from Whitman College, and aerospace engineering from the University of Southern California. And she's been with us a long time and is currently the project manager for the Voyager Interstellar Mission. And so, Susie, over to you.
Thanks, Ralph. Okay, as Ralph mentioned, I am a dual-hatted employee of the Jet Propulsion Laboratory. I am the Voyager project manager. I've had this job as a project manager since 2010. And I also, I'm in charge of the directorate at JPL where the Deep Space Network sits. And it's a good combination because you can never talk about Voyager without talking about long distance communications. And similarly, you can never talk about the DSN without talking about what's the furthest spacecraft you talk to, which is Voyager. So, and just one little other factoid about my background is when I graduated from Caltech in the mid 80s, my first job was on Voyager, and that was before the Uranus encounter. So I went off and did many other things after the Neptune encounter. Cassini and Spitzer and some other projects, but I came back in 2010 as a project manager, and I did not really expect that the mission would even be flying then. But it's great. It's a thrill to be part of Voyager and a lot of fun too. So next slide. Okay, first and foremost, I think, is to realize Voyager was never designed as a long duration mission. Voyager was designed as a planetary mission and really only a mission to Jupiter and Saturn. The level 1 requirements were for a Jupiter flyby and a Saturn flyby. There are 2 identical spacecraft. They are certainly not identical now, but at launch they were identical. And they were launched in 1977 when the Bee Gees were very, very popular, if you remember that group. But they were launched at a time where all the planets were aligned on the same side of the sun. So essentially, if your mission lasted, you could slingshot one of the spacecraft out, using gravity assist from Jupiter, Saturn, and then get to Uranus and get to Neptune in 12 years. And of course, that's what Voyager 2 did. Voyager 1 took a different trajectory. Voyager 1 had a close flyby, and I'm forgetting, but its trajectory took it up and out of the ecliptic plane. And then Voyager 2 past Neptune, its trajectory took it down and out of the ecliptic plane. So they're both spacecraft are going toward the nose of the heliosheath, if you want to think of it that way, but one is up out of the ecliptic plane and one is down out of the ecliptic plane. Now, since 1990, we were repurposed as a Voyager Interstellar Mission. And I realize this chart is a little bit out of date because that's not 29 years ago, but 31 years ago. So we have been exploring the heliosphere and now interstellar space for more than half of the mission. More like 2/3 of the mission has been an interstellar mission. And we switched from the planetary division to the heliophysics division right there in the early 90s as well. But what's important is there's 2 Voyagers are in situ taking data. And when you combine that data with that from missions like IBEX and even in some data from Cassini, you really get a better understanding of the properties that are ongoing in the heliosphere and now in the very local interstellar medium. So next slide. Okay, this is just a page you can pull up off of our website, which is listed on the bottom. The key thing here is, and I know that you Interstellar Probe folks understand these, but it's super long time round trip light time. Okay, we're pushing 2 days now to send a command to the spacecraft and hear back from the spacecraft that it executed that command. So that really drives the design of what you do and how you operate the spacecraft. You'll see that we are currently right now, Voyager 1 is 154 AU and Voyager 2 is 134, sorry, 128 AU from us here on Earth. We typically measure from the sun, since the Earth goes around the sun's a little more stable and the differences in distance aren't that much. Voyager 1 is the faster of the two spacecraft. It goes approximately 3.5 AU a year, where Voyager 2 is only going 3.2 AU a year. This is updated daily. So in case you need to give a presentation or something, you can find the latest stats on our website here. Let's go to the next slide. So science objectives, I think, are going to be very similar to what is being done for the Interstellar Probe. But some of the things I find interesting, and this is basically straight from our senior review proposal, is the shape of the heliosphere. Okay, we think of it as a more traditional comet shaped, but the data that Voyager's been getting, you can have a model that says it's more spherical, or even a model that says it's more croissant shaped, where the magnetic field of the interstellar medium is interacting with the magnetic field of the sun, and it makes the heliosphere more shaped with two lobes. So the question is, what's causing these variations, and why would there be these differences? And it's great fun to hear the modelers argue back and forth at our science team meetings about what they think is actually going on. Surprisingly, we're finding the heliopause in that area to be very dynamic and not the same between Voyager 1 and Voyager 2 and where they crossed. And it's very important that we have two spacecraft, because then we have two data points to try and fit models to. And it's very interesting, they see different things. So we're super fortunate that we actually have two healthy spacecraft operating. There's a question about the bow shock. Is it there? What would cause it to be there or not be there? And finally, there's the direct observation of galactic cosmic rays and modeling of the solar environment for cosmic rays, and just a lot of great questions that need trending data over time. You know, these spacecraft are traveling out just like they left the beach, and they're going through the waves out into the center of the ocean, and that wave structure changes as they go further out. So getting that data is very important. Next slide. Okay, quick refresher on the instruments. Let's see, Voyager 2 is a 3-axis stabilized spacecraft. It has 3 RTGs on it. We started with 478 watts of power at launch. We now have 238 watts of power. So that's a big driver is we lose 4 watts of power a year. And that's what's going to lose the mission. We're eventually going to run out of power. And I'll talk about how we manage that in a minute. But there's 4 instruments on Voyager 1 and 5 on Voyager 2. Voyager 2 has a plasma science instrument. It made a direct measurement of the change in plasma density when we crossed the heliopause. So we knew right away, versus Voyager 1, we didn't know right away. We had to kind of go back and infer the crossing from the data we saw. The 3 fields of particles instruments, LECP, CRS, and PLS, are all out on this long boom. And well, not the magnetometer boom you see to the left, but the boom on the right. So they get very cold when we turn off their instruments. And we've been real fortunate I'm sorry, when we turn off the heaters, each of the instruments has a heater, and to save power, we've been turning off the instrument heaters, and they've dropped in temperature by like 50 to 60 degrees C when we turn off an instrument heater. But so far, we've had great luck in that the instruments continue to operate at those much colder conditions, and the data needs some recalibration, but it's still good data. So we've been very fortunate with that. Let's go to the next slide. The next two slides are just a sort of a simple block diagram showing what's on and what's off. And for Voyager 1, the upper right is where we, that box in the upper right is where the instruments are. So for Voyager 1, the current status is the LACP heater is off. PLS actually failed back in the early 2000s and was turned off. But the next thing we're going to be doing on Voyager 1 is to turn off the CRS heater. That's going to happen in late 2022. And again, I mentioned these were fully redundant systems. They are not redundant now. You can see where the USO, we're on the backup USO for Voyager 1. The USO failed a long time ago, like close to launch, and we've been on the backup for more than 40 years. Next slide. Okay, same thing for Voyager 2. From an engineering perspective, the primary receiver on Voyager 2 failed early on. So we've been on the backup receiver on Voyager 2 for quite a while. Instrument-wise for Voyager 2, the CRS heater is off. The LACP main heater is off. We'll be turning off the PLS heater here in December. And that will be interesting to see when we do that, if the instrument keeps operating or not. So let's go to the next slide. Okay, I know that some of this has been mentioned over the course of your workshop and in the development of the ISP mission plan, but it's probably worth, telling you our experience from Voyager's standpoint. The round trip lifetime and the very low data rates, I didn't mention the data rates, but our nominal data rate on Voyager is 160 bits per second. When you have that, you really have to have a very autonomous spacecraft. You can't respond to anything quickly. If you think, if I put my JPL hat on, we have a lot of Mars missions, right? So you can send a command to Mars with a round trip lifetime of anywhere from 20 to 30 minutes, right? It means you can do the same thing. You can command multiple times over one DSN pass. Anytime we do a command to Voyager that we want to verify the downlink for, we actually need multiple DSN passes because it's spread out over nearly 2 days. So that's it makes life a little more complicated from a commanding perspective. We have a lot of repetitive blocks and repetitive sequence activities. So you just do a call where it's already built on board and it executes, say, once a quarter on its own. We have a big emphasis on fault protection because that spacecraft has to be able to stay in a safe state for weeks before we can really analyze any type of anomaly. Because the downlink rate is so small, we don't get much data to analyze any anomaly. We have a backup mission load in case we lose communications. And this was something that was done back in the planetary days, and we've kept it going for VIM. If our receiver fails, but our transmitter is still working, we'll be able to send data to the ground. The spacecraft will go into this backup mission mode and just keep continuing to send data back until it runs out of power. And we operate in a mode where everything is real time, with the exception of one high rate playback of PWS data. And basically, the spacecraft is always downlinking, and we only get the data when we have DSN antennas collecting it. Yeah, for the high rate data for PWS, that's the plasma wave subsystem. that high rate is only 1400 bits per second. So it's a lot more than 160 bits per second, but not a lot in the big scheme of data return. However, due to the distance of Voyager 1, and again, the high rate data only comes off of Voyager 1, but due to the distance, it takes a 70 meter and 3 34 meters all arrayed together to get that data down. And that's basically a whole complex. The DS is expanding. They are putting a 5th antenna at each complex, but that's not going to get completely built out over all 3 complexes until the early 2030s. And there's a lot of competition for DSN antennas. And I think I noticed that Michael mentioned this right before I got on here, but this is a mission that an interstellar probe is a mission that's going to go for decades. And when you think of that, that's generations of engineers. So knowledge capture and documentation is very important on a long duration mission. We're fortunate to have several of our flight team members who have been on Voyager for 35 plus years. And so they have a lot of knowledge just built up over time, not necessarily things that are written down, but things that they know about. I think you also need to have a good plan for cross-training engineers. When the planetary mission ended, when VIM started, there were about 50 or 60-ish engineers on the VIM mission. And then over time, his budget shrunk and well, I'll just say budget shrunk. We're down to 12 people on the project, 10 of which are engineers flying 2 spacecraft, which are not identical spacecraft anymore. So it's important that your engineers are cross-trained into multiple subsystems. We've done that quite a bit. We've also gotten recently, as people have retired, we've been able to get sort of what I would call the 2nd generation of Voyager engineers to come back and work on the project at the end of their careers, somewhat like myself, but people that worked in the planetary days went off and did literally something else for 30 years or closer to retirement, but are coming back to be part-time GDS engineer or part-time mission manager or something like that. And I think a lot of that is just due to the love of the mission. It's a great mission. Obviously, all of our documentation was originally in paper. We have boxes and boxes and boxes of paper. However, we did make a big effort to at least scan most of those documents and papers in so that they could be found electronically. But you lose things. We've moved office space, something to consider. Are you going to actually keep the same mission support area for 50 years? Probably not. We've moved offices several times, and every time you move, some box doesn't get delivered or some hardware test bed gets broken. So you have to consider those type of things that you won't always be able to keep the original documentation. And another key point I think that we found is that documentation conflicts with each other. We have launch documentation and we have planetary encounter documentation. And when we go back and look at those about how much power a subsystem takes or something, they're different. They're different. And then you try to figure out how to make sense of that so that you can move forward and assume when you turn off an instrument heater, it's going to give you this much power. We've been surprised. Let's just put it that way. We've been surprised about power gains when we've turned off instrument heaters. And I think it's important to maintain a list of contacts of retirees. They have the knowledge, so as long as they're willing to talk to you, keep in contact with that. Make a Rolodex of people that retire off of your project. Next slide. Our particular challenges, again, I've already mentioned that we have 2 spacecraft that started identical but are not identical now, so we need to be they're kind of like twins, and has the twin sisters have aged. One no longer hears and the other one is nearly blind, and so you've got to remember which has which ailment too. So good documentation and people that have worked on the project for a long time help with that. Every decision we make is related to power and thermal. We're losing power. We're turning off instruments, instrument heaters, and then instruments. We're also looking at more risky options we can do on the spacecraft to save power. And one of the discussions we've had is, as an example, is operating at a power margin below the discharge controller. Can we do that to extend the life of the mission? Can we power cycle instruments? These instruments have never been off. Can we power cycle instruments closer to the end of the mission in order to continue to get data from them? We also use some components solely as heaters. We have thrusters for our hydrazine that keep us, we're a 3-axis stabilized spacecraft. We need to keep that antenna pointed toward the Earth. If those hydrazine lines freeze, we'll likely lose our pointing and then lose our communications. So that's why we need to manage the thermal states as well. The DTR on Voyager 2 is on simply as a heater. It's where it's located, keeps the lines warm. So we didn't turn it all the way off. Obviously, our flight hardware is aging, but you know, your ground software is going to change, and that's going to be really tricky. I noticed that was one of the risks too. You're not going to be able to change anything on your spacecraft, but your ground software always has to be updated. There'll be new cybersecurity requirements, so you have to have a plan for keeping your ground software up to date. And for us, we have other challenges, such as we don't have a hardware test bed. We lost that a long time ago. We have a kind of limited software simulator. We have very limited memory on our spacecraft, and an antiquated programming language. So those are all, you know, other challenges that occur on long duration missions. Next slide, please. But we're getting great science, and I just wanted to point out one of our recent science highlights has to do with the plasma wave instruments. And this paper was published back in May, but they've been able to detect a very faint plasma emission, and this is just kind of a screenshot of of the data. And they were able to detect this by going back and using what I would call astrophysics data processing techniques on the Voyager data. And one of the fun things for me is I feel like Voyager has started as a planetary mission. It moved on to being a heliophysics mission, and now it's practically an astrophysics mission, right? You're out there in interstellar space. We've got guest investigators who are really astrophysicists, and it's great. It's great to see the progression of this mission. But the point here is we've got new and exciting science, and it's a reason to keep the mission going, and to continue it. If we go next. So just to wrap up, I think nobody could argue that Voyager is truly a remarkable mission, extremely robust design, and extremely dedicated engineers who operate it. There's a book called Voyager Tales, and in that book, it's firsthand accounts from the people that worked on Voyager and worked at JPL on the time. Everything from a project manager down to the cafeteria worker, you know, describing their feelings around Voyager. This was published after the Neptune encounter, but if you read through that, what you'll find out in the building of the mission, in the design of the mission, quite frequently they would use parts that were higher rated than they needed to be for a 4-year mission. But they wouldn't tell their bosses that they did that. They would just stick in a higher rated part, assuming that the cost wasn't too different. And I think that type of engineering and that type of forward looking to what the mission could be really made the spacecraft robust and gave it its longevity that it has today and that is displayed today. I'm not sure you can do that in today's environment. Everything is so cost constrained, but we were able to do that 44 years ago. And as far as the future of Voyager, we actually, I'll be even more optimistic because we've been really delving into trades, science trades and spacecraft trades. We could get out to 2030. The alternative, though, is we could break tomorrow. You really can't say that, but you don't know. But about a year from now, next year will be our 45th anniversary from launch. It's also the 10th anniversary of Voyager 1 crossing into interstellar space. So we at least deserve a good party. We're working with NASA on that. And I think now I would be comfortable saying we should easily get one spacecraft to last 50 years. Probably won't ever get out to 200 AU, but we should be out in the 170-ish, 180-ish range if we're lucky. It's about 30 more AU than where we are today. Yeah, I'm looking forward to more science from Voyager and just really what Voyager can do to help bring along the rest of heliophysics and astrophysics missions. So that's my closing thoughts. So I guess I can take questions now. Should I be reading them out of the chat box?
No, I got that for you. Thank you very much, Susie. It was great to see that. I think I have a new book to buy. Voyager Tales sounds fascinating. John Cooper writes in the Q&A, he says, Susie, many key project operations documents from Pioneer were never released for public access due to tech transfer rules and he says that you would have the same problem for Voyager. So process of project document release should be created early for Interstellar Probe. Are you already doing that with Voyager?
We have released some documents. We still are under ITAR control, like any other thing, though. So we certainly can't put out anything with command mnemonics. Sure. Even though they're so antiquated, I'm not sure anybody could do anything with them. But we occasionally get requests for stuff, and if it's something that's not under ITAR control, we could get documents and records to release them. Yeah.
I saw there's an interesting book out. It's the Haynes Manual. Are you familiar with these Haynes manuals?
Yeah. Oh, yeah. Actually, I am vaguely familiar with them. Yeah.
Yeah. So Haynes manuals, you buy, a 1970 Pontiac Ventura. You can buy a Haynes manual so you can figure out where the dipstick is and how to change the oil and which brake pads to put in. There's a Haynes manual for the Cassini-Huygens mission.
Yeah.
It's a great book with lots of cool stuff in it. And I wonder if that sort of thing for Voyager and others now would, it's got engineering drawings that have been allowed to be released and all kinds of stuff.
It took a long time for our engineering drawings to be able to be released. You could go on the web and find the engineering drawings before we could release them. So it was kind of silly to have them ITAR control when you could just go out on the web and find them. But
I've got a question here, actually. Okay. I'd love for you to take this question. Nibbin he's a student, he's from India, and he's been tuned in all week long. And he asks, do you have any special memory to share that you had with Carl Sagan for the Voyager mission? Congrats on 44 years in space on September 5th. So
yeah, I had Carl Sagan autograph his book Cosmos for me. That was kind of neat. So I had an autographed copy of that. And, I think anybody that worked on Voyager, the Neptune encounter was at that time viewed as pretty much the end of the mission. And the Planetary Society put on a big party at JPL where they actually had Chuck Berry come and play Johnny Be Good on the steps, and everybody was dancing, and Carl Sagan was up there dancing on the mall with Chuck Berry playing his song, and it was great. That's absolutely one of the best memories in my career. And
fantastic.
It was very special.
Michi asks, how do you make sure you don't lose the built up institutional knowledge with the people? You talked a little bit about this.
Yeah, I think having a good training program and and knowing that you're going to change out, if you know you have a long duration mission, which ISP certainly does, having a plan for how you're going to handle people moving on and off the project, and documentation, keeping documentation updated, and having a training plan so that somebody doesn't leave before the next apprentice engineer comes in. I think those are all very important things.
Yeah. Well, Susie, thank you very much for coming to be with us today. And I liked Michi's, Niven's congratulations on 44 years. That just came around recently. It's really great to have you here, and thanks for sharing everything you did today. Really appreciate it.
Thank you, Michael.
Okay. All right, everybody. We'll be back at 12:30, but not in this Zoom room. We're going to be moving to not the webinar format, but I'm sorry, at 1 o'clock. We'll be back at 1 o'clock. It is 12:30. We'll be back at 1 o'clock. There'll be a link in the chat for anybody to grab. You'll also have that in your email from this morning. At 1 p.m. we'll be in a Zoom room where Elena Provornikova is going to lead a discussion on next steps, and we're going to break out into some breakout rooms to talk about things that you believe we should be doing. The questions that we just got about longevity and planning and training are certainly the kinds of things that we'll be talking about. And then we'll wrap up with a small presentation at the end, just some last thoughts about legacy, policy, and how we get from here through the decadals and on into possibility of this being a mission that goes forward. Thanks, everybody, and we'll see you at 1 o'clock. We'll leave this Zoom open for a while so that you can pull that link and join us in the next Zoom room. Thank you.